I'm going to talk about current density in electromagnetic theory. I'm going to start by considering the standard definition we give for the current density, which is J is equal to rho v, and then I'm also going to discuss the fact that we often write in a conductor that J is equal to sigma E. So let's start with the first of these. Why do we say that J is equal to rho times V? The simplest way of looking at this is to consider a current flow with, let's say, uniform density, and just to think about a small tube of material. So we're assuming that we have a charge density, rho, in this volume, and we're going to assume that we've got the same charge density throughout space. And we'll assume that the average velocity, if you like, is given by V. Then in each unit time, we're going to draw out, that's not what I meant to do, let me put that line back in again, we're going to draw out a tube of length V per unit time, and we're going to have a cross-sectional area at the end here, dA, let's say. So the total charge in that cuboid, if you like, that rectangular volume, is given by the charge density rho multiplied by the volume, which is the velocity v and the cross-sectional area A. Now let's just think about one end of that volume, so the end that I've drawn here with the dA on it. The current flowing through that end in unit time is the total charge contained within that volume, and that's it, that's all it is. So the current flowing per unit time, obviously, the current flow, sorry, that's badly phrased, isn't it? The current flow is simply the charge per unit time. That's a better way of phrasing it. And we've just said that the charge in that volume is rho v dA, so that's therefore equal to the current. And we have a simple definition that the current density in 3 dimensions is given by I divided by the area we're considering, which in this case is, of course, I divided by dA. And now if we think about the directions, we can therefore say that the current density J is equal to rho, the charge density, multiplied by V, the velocity. And this has the correct dimensions. You should always check that formulae are dimensionally correct. So on the left-hand side we have charge per unit time per unit area. And on the right-hand side we have charge per unit volume multiplied by length over time. And so the length on the top there cancels with one of the elements of the volume, so we get charge per unit area per unit time. So it's at least reasonable. And this is a commonly accepted definition. Of course we are making various assumptions, various averages. We haven't even thought about the question of what happens if we have opposite signs on the charges, but that's actually not terribly important. You can set everything up in a normal way. So now why do we say that J is equal to sigma E? This is actually just another statement of Ohm's law, and it's directly equivalent to saying that V is equal to IR. We can come up with a justification using what's known as the Drude model. It's not a detailed and correct quantitative calculation, but it is at least useful and interesting. So let's go through this. We know that the Lorentz force on a charged particle is simply given by F is equal to Q into E plus V cross B. Now, in a typical conductor, we can neglect the effect of B, and we will do that for now. So now we have that the force F is equal to Q times the field E. Now let's think about what goes on. We know that there is a constant current flow. If you apply a force continually, you would get a constant acceleration, and therefore the velocity would increase over time. So we know there must be some other process going on in this system. And what we're going to say is that we have a constant force, which is the Lorentz force, but it is balanced by scattering in a conductor. And what we're going to say that you can have scattering from other atoms, from other electrons, and so you will have an average path length which we can characterize with something like a lambda, or you could have an average time between scattering events, which we will characterize with a tau. Of course, the two are going to be related. So what we're going to see is we're going to see a situation where a particle is accelerated over time, it then scatters, and so over a longer time period, the balance between the acceleration due to the electric field and the scattering events gives it a constant velocity. If you want to, you can think about driving in a city where there may be a gap in the traffic, at which point you accelerate rapidly. Hopefully there isn't an actual scattering event, because that would involve a car crash, but maybe you then have to brake in order to avoid such a thing. And over time you build up an average velocity through the city, which is a balance between the acceleration and the scattering events. So now we know that the force is equal to dp by dt, where p is the momentum. And so if we're thinking about averaging, we can say that the momentum is going to equal QE, that's the force, multiplied by tau, so that's effectively integrating over that scattering time period. That's an average, using the fact that, of course, P is equal to m times v, and we already know that J is equal to rho times v. We can write the following. So we're going to say that J is equal to rho times v, which is equal to P over m times rho, which is equal to Q E tau, rho over m. Or if you like, you can write that as rho Q tau over m multiplied by E. And now we might choose to give this little conglomerate the label of conductivity, sigma. And this is in essence the Drude model, which explains qualitatively what goes on in a metal. You can, if you want to, it's possible to relate the path length and lambda, tau, and a thermal velocity, because actually in many cases the thermal velocity of the electrons dominates, and come up with some material dependent predictions for what tau should be, but it doesn't really add anything in terms of our deeper understanding. This is just a way of understanding why we often find that J is equal to sigma E. So that's an empirical fact. It's expressed also in Ohm's law, V is equal to IR. So there we go. That's a brief overview of why we write J is equal to rho V, and also J is equal to sigma E in a conductor.